Hello. Hello everyone. Today again you're welcome to a revisions in wave on questions and answers. So we want to look at solve some questions in wave and light. So we expect that everyone will contribute and put their part to these various questions and answers. So we want to look at the multiple choice questions from the very beginning. Now the first question you see on the screen, it's repeatedly going to be shown like this. It says the following table shows some examples of waves. Which rows correctly list the natures of each of the wave type? So we're looking at we want to look at the row, which row correctly shows the answers. You look at the first one, we have the sound waves, we have the infrared wave, we have the red light waves. So we want to tell or look and see which of them is the correct one. Which of them is the correct one? Now the first one, sound wave. Is it a transverse wave? No. Sound wave is not a transverse wave. It's a longitudinal wave, right? And then the infrared or electromagnetic wave, they are transverse wave. Whether be it infrared, be it red light waves, be it visible light, be it microwave, be it radio waves, be it X-ray, be it gamma ray, or electromagnetic wave, they are transverse wave. So the option, the correct option will obviously be what? B, because sound wave is a longitudinal wave, and infrared is a transverse wave, and red light is also a transverse wave. So the correct answer will be B. Yo. So we'll move on to the next question. Quickly, move on to the next question. Is that okay? So let's see what this question has for us. Can you read the question?
What is the definition of the word amplitude?
Okay, here we have what is the definition of the word amplitude. Okay, amplitude. So we've studied this topic, we should know the definition of the word amplitude. Okay?
A number of...
Okay, now let's take a look at it. It says the first one says the number of complete waves that pass a point per second. Is that amplitude? No, that's not amplitude. It's not the number of complete waves that pass a point per second. Okay, then the distance from the peak of one wave to the peak of an adjacent wave. Yeah, that's the distance from the peak of one wave to the peak of an adjacent wave. That is the definition, right? That could be. Now, but you have to read all the options to know which of the options is most likely correct or more correct in this regard. The third one, the distance from the equilibrium positions of a peak plus the same distance from a trough. Okay, you see, C and D now you have to be careful in why choosing your answer. The distance from the equilibrium position is, you know, this is a wave, for example, this is the equilibrium position. Okay, and then you have the peak back to the equilibrium position and then back to this place like this. This is a wave. Okay, this is a transverse wave. This is a transverse wave. Okay, for example, the distance from here, the distance from this place to this place is amplitude, right? So from the equilibrium position to the peak, to this peak, which is crest. This is a crest or peak. We can use peak or we use crest. We can use peak or we use crest. So this is an amplitude. So if we look at C and B again and see which one is more correct in this regard. So it says the maximum distance from the equilibrium position of any point on the wave. The maximum distance from the equilibrium position or equilibrium position of any points on the wave. Now remember, this is the equilibrium position. This is the equilibrium position. This line, this horizontal line is the equilibrium. Okay, is the equilibrium position. This horizontal line is the equilibrium position. So now you look again between B, C, and D. Which one is the correct answer? Between B, C, and D, which one is the correct? Then the maximum distance from the equilibrium position of any point on the wave. D is the correct answer. Yes, that's what we call amplitude. Now let's move to the next question. Okay. Now let's take a look at this question. Okay, you say, what is the name given to the effect that allows the wavefront to reach point X? What is the name given to the effect that allows the wavefront to reach point X on or shown on the diagram? Right? Diffraction. Diffraction. Because when this is a barrier, there's a gap between two barriers. So whenever a wave passes through a narrow gap between two barriers, then it will diffract. It will diffract. Diffraction means it is spreading out. To spread out. Okay, it will diffract. So one of it will pass through point S, one will go straight, and one will go this way. Okay, that's called diffraction. Look for the option C, right? C is the correct answer in this regard. This C. Diffraction is the correct answer in this regard. Now let's move to the next question. Is it which 2 points on the wave are exactly one wavelength apart? Which 2 points are exactly one wavelength apart?
Q and S?
Yes, Q and S. Which 2 points are exactly one wavelength apart? Is Q from here till the end of this. You see, this is the end of this first segment of the wave, half of the wave, and then this is the end of the other one. So it's Q and S. But if they put P and there was also one here in the middle, would have been the correct answer. Okay, so it's P and it's Q and S. So look for the option that is Q and S. C, right?
Yes.
Q and S is C. So this is our answer. Now we move on, okay, to the next question. We cannot view, right? The Yungo Shoko. Let's move on. Okay, the Yungo Shoko. Let's move on, students. Let's see what we have for the next question. The next question says, what is the unit of wave speed? Speed of wave. What's the unit?
Hertz. Hertz.
Hertz is frequency. You go show all of you. Okay? Hertz is frequency. What's the unit of wave speed? Speed.
Meter per second.
Meter per second. Meters per second. D is the correct answer. Meter per second. We have more questions? Only 5? Okay.
These are
Okay, we go to the next level, medium question. The first one we studied are the easy questions. So imagine if you get 5/5, you clap for yourself. It means you're progressive and you're moving very speedily, okay? Now let's move on to the next one, the medium one. Let's move to the next one, the medium one, quickly.
water waves travel from deeper water to move shallow water. This causes them to refract, which wave property always remains the same when refraction occurs. A. Wavelength, B. Frequency, C. Amplitude, and D. Speed. Water waves travel from deeper water.
Now we see this question, it says water waves travels from deeper water to more shallow water. From deep water to more shallow water. Now this causes them to refract. Yes, refraction when you change a medium. When a wave travels from a medium, deeper water to a shallower water, when you travel from deeper water to a shallower water, the wave will refract. Let's say these are the wave front, what we call the wave front. Okay, and then the next one you see will start to shallow water. The wave front will now be closer, right? Okay, so there's a refraction when the wave is coming like this. When the wave is coming like this, when it gets to shallow water, it will refract. It will refract. Start going this way. Start going this way to refract. Okay? So this is what the wave, from the deep water to shallow water, the wave front will refract. Now let's take a look at the characteristics. What they're going to ask us. Is a water wave travel from deeper water to more shallow water. This causes them to refract. Which wave properties always remain the same when refraction occurs? Which wave property always remain the same when the refraction occurs? Is it the wavelength? Is it the frequency? Is it the amplitude? Is it the speed? Of course, speed is different now. Speed is different, slower, it becomes slower. So, wavelength, is it frequency? Is it frequency? Is it amplitude? Quickly. Going.
Frequency.
Going. Yes, frequency. Because I got it. Frequency. Okay, the one that is it which wave property always remain the same when the refraction occurs? Frequency will remain the same. Wavelength will be different. You know the meaning of wavelength, right?
Yes.
So you see this, you can see this wavelength. They are different from the wavelength here. The distance between these wavefronts. They are your wavelength. This is a wavelength. This is a wavelength. Here the wavelength now differs. You can see it's but the frequency will be same. Frequency will be same. The frequency will be established same. So we'll move on to the next question. Okay, the answer is frequency. Frequency will remain same. Move to the next question. Okay, now we're here. Read and answer the question.
Which of the following waves are longitudinal? A. Radio waves from a radio broadcaster. B. Infrared waves from an oven. C. Sound waves from a guitar. D. Water waves on a lake. Obviously C. Because C is longitudinal. C is longitudinal. So the answer is C. It's like question 1. Question number 3. Which of the following statements about sound waves is incorrect? A. Sound waves are longitudinal. That is correct. Sound waves transfer energy away from the source. Sound waves push air away from the source. Sound waves cause objects to vibrate. I don't think this is the answer. This sounds correct. It sounds like
Sound goes up to my brain and they are longitudinal, so it's neither A or B.
it's better it's B or C.
Sound and push air away from the source. I think C is wrong.
C is wrong.
Hey, do not speak.
Oh, Jefferson.
The speed of the wave is doubled. The frequency remains the same. What happens to the wavelength of the wave?
It doubles, it halves, it remains the same, it becomes 4 times as
The
large.
speed of a wave is doubled. The frequency remains the same.
What happens to the wavelength of the wave? Wait, the speed wave is doubled. The frequency remains the same. What happens to the wavelength?
Double speed is not because one wave.
Do you think it doubles? You think it's A?
Yeah, they say the speed of a wave is doubled. Speed of a wave means the speed, and the frequency remains the same. The frequency is still the same. And then what happens to the wavelength? So it doubles. A.
Okay, I also think it's A. So let's go to question 5.
That question 4.
Yeah, we're done.
We even did question 3.
The speed. Which of the following statement about this sound wave is incorrect? Sound waves are longitudinal. That one is correct. So it's not incorrect. Sound waves transfer energy away from the source. Sound wave transfer energy, yes. Always transfer energy away from. That's correct. Sound wave pushes air away from the source. Sound, yeah, yes. Sound wave cause objects to vibrate. Yes. All wave cause sound wave cause object to vibrate. So we go back. A sound wave transfer energy away from the source. Which one did you choose?
Wait, I picked C.
Sound wave push air away from the source. As I'm talking, to push air away, right? Push air, that's also correct. Sound wave cause objects to vibrate. Sound wave cause object to vibrate. No, it is the vibration that causes the sound wave. Yeah, this is correct. Vibration causes sound wave. Sound is caused by vibration, not sound cause object. You understand?
Yeah.
Okay. Now we move on to the next one. The speed of a wave is doubled. You double the speed, the frequency remains the same, right? You double the speed, the frequency remains the same. What happens to the wavelength of the wave? Remember the relationship between this concept. Speed, you can just write the formula. Speed is equal to the wavelength, which we represent as lambda, multiplied by the frequency. Okay, you can see that the speed is directly proportional to this. Okay, so you say the speed increases. What happens to the speed? You say the speed of a wave is doubled. You increase the speed. That means you double it times 2. The frequency remains the same. Frequency is a constant. What happens to the wavelength? It will also increase, right? Because yeah, it doubles. So A. Okay, good, great. Will you let us see? There you go, Shoko. Okay. Now let's move on quickly to the next question. Okay, somehow we have seen this before. Shallow water, deep water. Somehow I have drawn this before, right? Somehow draw this before. So when water waves travels from deeper water into a more shallow water, they refract. We've kind of said something like this. They refract. Why does the wave change direction in the manner it did? Because of refraction, right? Now they say the wave speed increases. No, the speed does not increase. The wave speed decreases. Yes. So when you get to shallow water, it decreases. Frequency increases. Frequency no. The speed there decreases, right? Yes. Frequency is constant. The speed there, the speed decreases. That's why. Is that okay? Yes. So we move on. We're done with the medium question. Now we're going to the super hard questions. Okay, we're going to the super hard questions. So you're going to try. This one, everyone, we're going to take a calculation, a calculator, we're going to calculate something. Okay? We're going to calculate something. Get ready, everybody. We're going to do the calculation now. The one they call the hard ones are the one that involves you to make calculation. I've given you the formula of speed. We say speed. We say speed. We say speed. We say speed is given as speed v is equals to the wavelength multiplied by the frequency. We can also use this formula. We can also use this formula. We say speed. We say speed. We say speed is equal to the lambda. Okay, excuse me, 1 minute. We say speed is equal to lambda, which is wavelength, multiplied by 1 over the time period. 1 over the time period. 1 over the time period. So we can call this equation 1, equation 2. We call this one equation 1. We can call this equation 2 for calculating speed. For calculating speed in a wave. Also for light wave, not only wave, also for light. We can use the same formula. Okay, this is equation 2. Now let's take a look at this very first question. Can we take a look at this very first question? It said the sound wave travel at a speed of 1,500 meters per second through a substance. Their wavelength is 5.0 centimeter. So can we convert this 5.0 centimeter to meter? What is the frequency of the wave? Because we have to put all the units in their standard form. So 5 centimeter, we're going to change 5 centimeter to meter because the speed is given in what? Was it given in, you check the speed was given in meter per second. So we must change this one to meter, not centimeter. Since the speed is 1,500 meters per second, we have to change this one to meter. We have to change the centimeter to meter. Can we change this one? Now we say the speed V is given to us as 1,500 meters per second. 1,500 meter per second. Meter per second. Okay, 1,500 meters per second. Now we say, what else is given? We don't know the frequency, but we know the wavelength. The wavelength is 5 centimeters. So we're going to convert this 5 centimeters. We're going to convert this 5 centimeters to meter. We're going to convert 5 centimeters to meter. How do we convert 5 centimeters to meter? We just say 5 divided by 100. We just say 5 divided by 100. We get 0.05. Am I right? We get 0.05 meter. So this gives us 0.05 meter. 0.05 meter. This is our, because this is all that is required from you. And then once you've done that, remember you're looking for frequency. You say speed is equals to lambda multiplied by frequency. Lambda means the wavelength, is a Greek word. This lambda is a Greek word which represents the wavelength. Lambda multiplied by frequency. So if you're looking for frequency, you make frequency the subject of formula. You make frequency the subject of formula by saying frequency equals to the speed divided by wavelength. Frequency equals to speed divided by the wavelength, right? So which is equal to 1,500, which is the speed, 1,500, which is the speed of the wave, divided by the wavelength. The wavelength is 0.0. The wavelength is 0.05. So 1,500 divided by 0.05, you get what? You get what? We get 30,000. Okay, the frequency is 30,000. You know, this is called 30,000 hertz. This is 30,000 hertz. Now we can put it in kilohertz in order to make the number not too bogus, not too big. Okay, this is 30,000 hertz. Remember, you have to put the unit of anything you do. Hertz is Hz, is the unit of frequency. 30,000 hertz. Now this 30,000 hertz, if you want to put in kilohertz, you divide by 1,000. So if you divide by 1,000, you get 30 kilohertz. If you divide this number by 1,000, you get 30 kilohertz. So we go and check the option now. You will see any option that has 30 kilohertz is the right answer to this question. Is the right answer to this question. So we come. The first one is 30 kilohertz, which is the right answer. This is 300 hertz. No. 7.5. No. The answer is A. The answer to this one is A. So this is how we do the calculation. Now let's say another question. Probably. Okay. Are we ready for this question? Take a look at this question. It says the diagrams below shows the wavefront. It shows the wavefront diagram of light as it passes from glass to air. They are magnified many times. Which diagram correctly shows what happens to the wavefronts? Which diagram correctly shows what happens to the wavefronts as they pass the glass to air boundary? Glass to air, from the denser to the less dense. From the denser medium to a less dense medium. There must be refraction. There must be refraction. The denser one will have a bigger wavefront. The denser one, B is wrong because look at all the wavefronts are all equal. All the wavefronts, that's the distance from one line to the next line, they all equal throughout, whether from the deeper one and from the. So this is not correct. This is not correct. Okay, this is not correct. A is wrong, and there's no refraction. There's no refraction of the wave. B is wrong. Now let's see A. You can see that the wavefronts are different. From the glass, you can see, and then to air, you can see. And there's refraction. So A could be an option. But let's look at C. C is wrong, though there is smaller wavefront in there, but there's no refraction. C is wrong. D, look at D. D also is wrong, right? D, the kind of refraction doesn't exist. We've not seen this type of refraction before. You don't refract like this. So D is wrong. So the correct answer is A. Correct answer is A, from glass and then to air it refracts. So A is the correct answer to this question. Is that okay? Now we move on to the next question as quickly as possible. The diagram shows a plain water wave approaching a gap as viewed from the above. Okay? A plain water wave as viewed from. the gap is very wide, so the diffraction will be little. There will be no much diffraction, because once the gap between the barriers is big, is bigger than the wavefront, then there will be little diffraction. There will be no serious diffraction. There will be little diffraction. Is that okay? So the diagram shows a plain water wave approaching a gap as viewed from above. Okay, this is the wavefront. These are the wavefronts. Now, how could the situation be changed so that the waves on the far side of the gap do not spread out as far? They just, if you don't want them to spread out as far, you increase the gap between there. You increase the gap between the barriers. You increase the gap between. He said decrease the speed of the wave but keep their wavelength the same. No, I don't think so. Increase the speed of the wave but keep their wavelength. Make the gap a little smaller, make the gap a little bigger, make the gap a little bigger. If you don't want much diffraction, make the gap a little bigger, right? So we move on to the next one. So we've answered this one. Now we move on to the fourth question, the hard side. Here, I think here also is about calculation. We say a small child throws a stone into a very still pond. Now where the stone hits the water, the wave travels outwards in a circular pattern until they reach the size of the pond. Now, in a very uncharacteristic move for a small child, he notices that 6 waves arrive in time of 3.2 seconds. Then the child has a remarkably accurate internal clock. So 3 significant figure, what's the frequency of the wave? What will be the frequency of the wave? Frequency is 1 over time period. Okay? Since the child knows the time period is 3.2. Say 1 divided by 3.2. What do you get? 1 divided by 3.2 will be the frequency of the wave. Because frequency okay? Let's read the question again. Maybe there's other information we need. Oh, there are 6 waves, right? So multiply by what the answer you get, multiply by 6. .875, yeah, which is 1.88, which is 1.88. Okay, so we get 1.88 as our answer. Why? We have to multiply by 6. There are 6 different waves, right? That's according to the question. The first thing we do, is that the frequency is equal to 1 over time period. The frequency is equal to 1 over time period. Frequency equals to 1 over time period. So which is 1 all over, the time period is 3.2. 1 all over 3.2. Which gave us 0. We got 0. What? You still remember? 0.3. 0.3125. 3125. Because there are 6 waves, we multiply by 6. Multiply by 6. Multiply by 6, and that will give us 1.88. 1.88 Hz. That will give us 1.88 Hz. Is that okay? Do we understand? Do we understand? Yes. Okay, great. Now we move on to the last but not the least for today, which is this one. So I leave you to answer this one quickly. It says, with skillful use of particular laboratory equipment, water can be used to demonstrate reflection, refractions, and diffraction. For each of these, which rows shows whether or not the wavelength of the water waves changes. Which row shows that the wavelength of the water wave changes. In reflection, does the wavelength changes? In refraction? In diffraction?
D.
Right? So
Yeah,
which one
D.
is the correct one?
D.
B?
D. D.
D. So reflection does not change, refraction change, the wavelength change. diffraction. Okay, D, right? D, the most correct answer. So with this, we've come to the end of our today's class. Thank you for joining us.